Welcome to Chapter 9, Acid and Base Chemistry. So we can see from the beginning slide all of the different topics that we'll be learning. It is quite a large amount of content, so bear with me. This will probably be in 2 sections because there is so much content. So use this list as a checklist. As you master these concepts, check them off. When you get ready to study for the unit exam, this is one of 3 chapters on this unit exam, so you can take a look at the list and see what you need to look over. All right, let's begin. So first we want to introduce acids and bases, and there's several definitions that are used to define an acid and a base. One of the earlier definitions that was given by the name of Arrhenius. And Arrhenius said that an acid is a substance that contains a hydrogen atom and it dissolves in water to form a hydrogen ion. So we write hydrogen ion with a capital H plus sign. And the equation shown here of hydrochloric acid, this, according to Arrhenius's definition, hydrochloric acid would be an acid because it contains a hydrogen. And notice that on the reactant side it turned into a hydrogen ion. And Arrhenius said that a base had to contain a hydroxide ion, and it dissolves in water to form the hydroxide ion, OH. And so sodium hydroxide, as you see here, is a common Arrhenius base because when dissolved in water, it forms the OH. However, this definition is limited and sometimes incorrect. So when that happens in science, typically a new definition is proposed and tested. And so the most widely used definition today is called the Bronsted-Lowry definition. And Bronsted-Lowry, 2 men, worked together, and they took Arrhenius's definition, which was the current definition of the day, and just revised it, made it more specific. They said that a Bronsted-Lowry acid is a proton donor, and a proton is given the symbol of H+. Now you may wonder why H plus means proton. Well, when we think about the hydrogen atom, we know that hydrogen has 1 proton. And if you look at your periodic table, you see that the average atomic mass is also 1. So if you remember correctly, the number of protons and neutrons in the nucleus determines the mass of the atom. And so since the atomic number is 1 and the mass is 1, that means the only thing in the nucleus of a hydrogen atom is a proton. And so if the hydrogen atom were to lose its 1 electron, the only thing it would have left is the proton in its nucleus. And so that's why this symbol is given here, and H plus means that there's only a proton left. The plus sign came from losing the electron, and all that's left is a proton, and a proton has a positive charge. So that's H plus is often used as a symbol for a proton. A Bronsted-Lowry base is a proton acceptor. So the acid donates the proton and the base accepts the proton. And so we see this happening here. HCl, just like Arrhenius's definition, HCl is a Bronsted-Lowry acid because when it donates its proton, as you see here, the proton or the H from HCl is given away, and on the other side we're just left with the Cl. And this H was given to the water, which turns into H3O+. So the acid is going to donate the proton, and the base, in this case water, is going to accept the proton. So hydrochloric is the Bronsted-Lowry acid, and water is the Bronsted-Lowry base. A Bronsted-Lowry base must contain a hydrogen atom. Bronsted-Lowry acid must contain a hydrogen atom. Some common Bronsted-Lowry acids. These are given the symbol HA. That would be hydrochloric acid, hydrobromic acid, nitric acid, sulfuric acid, and acetic acid. Let's just write out those formulas. So we have HCl, HBr, HNO3, H2SO4, and the last one is HC2H3O2. You'll notice that these names, some may look familiar to you, some are named just from the anions from the periodic table, others are named after polyatomic anions. And so let's talk about the name just a moment. The names of common acids are derived from the anions that they form when they dissolve in water. Remember, anions have a negative charge and they're written second in a chemical formula. You start with a cation followed by an anion. So there are some rules to follow when naming acids. Anions whose name ends in the suffix IDE, then you're going to add to the acid name, you're going to add the prefix hydro, and then change the IDE to IC. So if the anion ends in "ide," like in chloride, then we're going to add the prefix hydro and change "ide" to "ic." So this becomes hydrochloric acid. On the other hand, sometimes you have polyatomic ions. Polyatomic ions whose names end in "ate," you will change the ending "ate" to "ic," and then you'll have the acid name. So notice we have sulfate, ends in "ate." All we did was change the "ate" to "ic," and now we have sulfuric acid. If the polyatomic ion names in "ite," we're going to change that. We're going to change the "ite" to "ose," O-U-S. And so here's an example. Sulfite becomes sulfurous acid. So here's the deal with naming. There's basically two types of acids. There are binary acids. So I'll write it up here, binary acids. And there are oxy acids. Binary acids, well, let me just back up a second. We said before that all acids have hydrogen. So in an acid name or an acid formula, it always starts with hydrogen. So that's a given. All acids start with hydrogen. So maybe make a note of that. All acids start with hydrogen. So when you're writing formulas and it's an acid, you know the first element is going to be hydrogen. All right, if it's a binary acid, that H is going to be followed by one other element. Bi means two, so you're going to have H and you're going to have one other thing. And so it's going to be a single element, typically from group 17, one of your halogens. And notice there are no oxygens. Binary acids do not have oxygen. And so it starts with hydro, ends with ic, and you add the word acid. So you could have HBr, hydrobromic acid, HI, hydroiodic acid, HF, hydrofluoric acid, and so on. All right, and then the second type of acid is called an oxy acid. And guess what? They contain oxygen. So both of these examples are oxy acids. Sulfuric acid has O's. Sulfurous acid has O's. So remember, they're named based on the anions. So if it has a polyatomic ion as an anion, if you look at your polyatomic ion list, all of those have oxygen. And so instead of the prefix hydro, we don't use hydro. So I like to say hydro means no oxygen, no O's. Hydro means no O's. So when I see the prefix hydro, I know there's not going to be any O's in my acid formula. If I do have oxygen, I cannot use hydro because hydro means no O's. Okay, so we see that we have a polyatomic ion that ends in 8. I simply took that sulfate, dropped the ending, and changed it to ic, sulfuric acid. If the polyatomic ion ends in ite, I drop that and replace it with O's, sulfurous acid. So again, two types of acids, binary acids, oxyacids, they're named differently. All right, let's move on. We can have different types of acids depending on how many protons they have to donate. So if we have something called a monoprotic acid, that means it only has one hydrogen to donate, like hydrochloric, only one hydrogen. Or we can have diprotic. That means it has two acids, two H's to donate, so like H2SO4. That's a diprotic acid. And then finally we can have triprotic, sometimes called polyprotic. And yes, that does mean 3, like phosphoric acid is a triprotic acid. It says a Bronsted-Lowry acid may be neutral, meaning no charge, or it may carry a net positive or negative charge, as you see here. So this is called hydronium ion. So notice it has a positive charge. And then HSO4 is the acid left after one hydrogen has been donated from H2SO4. And so just keep in mind that a Bronsted-Lowry base is a proton acceptor. So it must be able to form a bond to a proton. A Bronsted-Lowry base is a proton acceptor. A base must contain a lone pair of electrons that can be used to form a new bond to the proton that it is about to accept. So let's take a look at what that looks like. A very common Bronsted-Lowry base is NH3. This is ammonia, NH3. When we draw the Lewis structure for ammonia, it looks like this. And you see there is a pair of electrons at the top, and that is available for a hydrogen to be attached. So in this equation, you see ammonia is dissolved in water, that one of the hydrogens from the water, which would make water an acid by definition, one of these hydrogen atoms is released and added to NH3, and now we have NH4 plus ammonium. And so this is a common, very common Bronsted-Lowry base. So lone pairs make these neutral compounds bases. So we have ammonium, water can be a base as well. The OH is the base in each of these metal salts. So we have sodium hydroxide, that is the salt, the base part is the OH. We have potassium hydroxide, magnesium hydroxide, and calcium hydroxide. So these are some common Bronsted-Lowry bases. All right, when we have a Bronsted-Lowry reaction, or a reaction between a Bronsted-Lowry acid and a base, we have something interesting happen. And so we see the acid and bases are labeled, and notice the acid, HA, is going to give up its hydrogen, that's the definition of an acid, and turn into A-. The A- is a result of losing that hydrogen ion. And so it's given a special name showing that they go together. We have an acid-base pair. We have an acid and its conjugate base. So the product formed by loss of a proton from an acid is called its conjugate base. And the same thing happens with the base. So the base here is given the letter B. Notice it has a lone pair of electrons ready to accept the hydrogen, and so on this side we see that has happened. And we have a base and its conjugate acid. And so what we call these conjugate acid-base pairs, and they always go together. An acid always has a conjugate base, and a base always has its conjugate acid. And so because of that, or based on that, we can pick out conjugate acid-base pairs. So this equation is an example of some actual compounds. We see hydrobromic acid loses its hydrogen and becomes Br-, and so we say that HBr and Br- are conjugate acid pairs. They go together. And on the other hand, we see the base is water, and it becomes the hydronium ion, H3O+. So again, these are conjugate acid pairs. If we look closely at these pairs, we see that the only difference between the two is one hydrogen. So in our first pairing, we have HBr, and then on the other side, Br. So that HBr lost a hydrogen and turned into Br. On the other hand, we have the water. It lost a hydrogen and turned into H3O+. I'm sorry, it didn't lose. I said that wrong. H2O+ gained a hydrogen and turned into H3O. Let me say that one more time. H2O gained a hydrogen and turned into H3O+. And so the net charge must be the same on both sides of the equation. So when a species gains a proton, it gains a positive charge. And when a species loses a proton, it effectively gains a negative charge, if you will. And so this works to keep the charge the same on both sides. So these always work in tandem with each other, conjugate acid-base pairs. So we talked a little bit about water. Water is something called an amphoteric compound, meaning that it contains both hydrogen and a lone pair of electrons, and it can be either an acid or a base. And so in the first example, we see water acting as a base because it's going to accept the hydrogen and turn into H3O+, or it can act as an acid and turn into OH-. So water can go either way. The splitting apart of a covalent compound, or ionic compound for that matter, into its ions has a kind of a fancy word. It's called dissociation. That's a fancy word for just dissolving. So when we split these molecules into individual ions, it's called dissociation. So anytime we have a strong acid that dissolves in water, 100% of that acid dissociates into ions. So hydrochloric acid is a strong acid. We're showing it being dissolved in water, and 100% of HCl is going to break apart into ions. And notice in this equation we have a single arrow. Just this reaction is going to go in one direction. All of the HCl is going to turn into ions. So this single reaction error, because the product is greatly favored at equilibrium. So we'll talk a little bit more about equilibrium as we move through. There are 6 common strong acids, And you can, if you have a periodic table handy, it's helpful to find where these, at least 3 of these are located, and it'll help you remember maybe which are strong acids. And so if it's not on this list, it's a weak acid, and it's going to be important that you know the difference. So HCl, notice that chloride, the Cl anion, is in group 17. If we keep going down, we have HBr, I'm going down period 17, and lastly HI. So these 3 anions paired with hydrogen are going to make strong acids, which mean they completely dissociate in water. There are 3 more that are recognized as strong acids: HNO3, H2SO4, and HClO3. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid. This one is called nitric acid, sulfuric acid, and hydrochloric acid. Sorry, chloric acid. This is just chloric acid. Okay, so those are the strong acids. And again, if it's not on this list, if it's not one of these 6, then it's a weak acid. When a weak acid dissolves in water, only a small fraction of its parts turn into ions. And this is going to make a difference when we start calculating pH. We need to know if we're working with a strong acid or a weak acid, and that will determine how we solve for the pH. And notice when we look at an equation, we see something different. Instead of a single arrow, we have an arrow going in both directions, meaning that this is at equilibrium. So the blank should be unequal. Unequal reaction arrows are used because the reactions are usually favored, the reactants, are usually favored at equilibrium. So notice the length of the arrow is, the longer arrow is pointing to the reactants, and that just means that this at equilibrium, this reaction favors the reactants. You're going to have more reactants than products. Here are some common weak acids. We have phosphoric acid, hydrofluoric acid, carbonic acid, and hydrocyanic acid. No need to memorize these. I would concentrate on memorizing these 6 strong acids. And if it's not on the strong acid list, then it's going to be a weak acid. So here are some pictures of what we mean by dissociation. So the first picture is a strong acid. And the strong acid here is HCl, and we can see that it has completely dissociated. You don't see any HCl still together. They're all broken apart into their ions. Notice where the H went. The H hooked onto the water and became H3O+, and then you have Cl- floating around in solution. Let's compare that to the other diagram. This is a weak acid. This is acetic acid. I always write it like this. This makes more sense to my brain. So the weak acid is only partially dissociated, and so we see a few H3O+ and acetate ion, but mostly they're still all tied together into acetic acid. So just a difference in how they dissolve in water. All right, let's talk about bases on the other hand. So when a strong base dissolves in water, 100% of that base dissociates into ions. So sodium hydroxide is a strong base, and we see a single arrow, and we know that it goes to completion, or all of the ions dissociate. So how do you recognize a strong base? Well, that's anything from group 1 on the periodic table, or group 2. If you have one of those metals from group 1 or group 2 paired with hydroxide, then you're going to have a strong base. There are 2 exceptions to that, 2 exceptions. Those exceptions are Be beryllium hydroxide and magnesium hydroxide. These are considered weak bases. So group 1 and group 2 metals paired with OH, except for magnesium and beryllium. So when a weak base dissolves in water, just like with a weak acid, only a small fraction of that base dissociates. A common weak base is ammonia. It's going to dissociate slightly into ammonium and OH. And so we see a picture of what's happening here. So we have sodium hydroxide, which we said was a strong base. And in the picture we can see sodium and hydroxide are split into their individual ions. But when you have the weak base, most of your NH3 are still intact. So we can see all of those NH3s that are still intact have not dissolved. There are a few that have, so only a small fraction of those will actually dissociate. All right, let's go back to our conjugate acid-base pairs. So it says a strong acid readily donates a proton. And when it does, it's going to form a weak conjugate base. So strong acid forms a weak conjugate base. And a strong base readily accepts that proton, and it will form a weak conjugate acid. So the stronger the acid, the weaker the conjugate. And the other scenario is true. The stronger the base, the weaker the conjugate acid. Here you have a table of relative strengths. I don't think it's necessary to memorize the table, but you can definitely look through and see. If this is needed in a problem, it would give you the table. It wouldn't, I don't believe it would expect you to memorize that. So just something to take a look at. And so we can use acid-base strength to predict the direction of the equilibrium. All right, I'm going to have to pause the video.